Welcome to our second podcast of our energy unit. So far, in the very beginning, we talked about 4 different ways we're going to be finding energy. In class, we looked at Hess's law, where you can rearrange your equations to get them to add to the overall, and whatever you do, remember whatever you did the reaction, that's what you had to do the energy. Then we used standard heats of formation, really important, products minus reactants. Now we're going to look at our third way, which is everybody's favorite, stoichiometry. Because energy is part of every reaction, remember that if energy is produced, given off, released, all meaning the same things, it's a product. If it's a product, the energy is exothermic. And we're at the top of page 7, if you didn't find this in the packet. It's exothermic, produced. Okay, what happens to the temperature? Remember, and this is what's also very important to know, the temperature goes up in an exothermic reaction because it is the reaction, the system is losing energy to the surroundings. We always take our measurements in the surroundings. If energy then is taken in, or is it a reactant, or is absorbed, all meaning the same thing, then we say it's endothermic. And endothermic reactions get colder. So the temperature goes down because the reaction, the system is taking the energy. So what you are seeing is the lack of energy in the surroundings, and it gets colder. So that means energy can be part of the reactions. Now a couple things in different ways we're going to see it. Look at again. Here's my arrow. So heat, what's happening to it? Heat is a product. It is produced. Another way we would write it, we would say negative 250 kilojoules. KJ, remember? Kilojoules. Because joules is your energy. Or we would say different things I could ask you. It is exothermic. Remember, the negative quantity of energy just is, again, it's been given off. It's still a lot of energy. The negative just means it's been released. Well, look what this is telling you then. We can do all the kinds of mole ratios. Because, same thing, this is a 1. That's what I'm looking at here. Remember when we have our mole ratios, this is where they come from. So every 1 mole of glucose releases 2,560 kilojoules. Let me try that again. So what else do we know? Well, for every 6 moles of oxygen, you also release 2,560 kilojoules. You could say, well, for every, you can have it on top, for every 2,560 kilojoules of heat, you have also 6 moles of carbon dioxide. We can set up any mole ratio with heat just like we set up any of our other mole ratios. But notice it's a mole, so if I don't have moles, that's the problem. We're going to have to get to, if I have grams, we'll have to still convert to moles. So how much heat's released when 1 mole? Well, for every 1 mole, so this is my given. So for 1 mole of glucose, C6H12O6. Now if this was a multiple choice, you wouldn't even have to show work. But this is how this is set up. Go to your balanced equation. Well, for every 1 mole of glucose, you get 2,560 kilojoules. Easy math, 2,560 kilojoules. Okay, look at the other problem. So how much heat is released? And again, you don't have to say, well, you could say this much released, or you can use the word, you could put positive, and you say that much kilojoules released. The negative sign takes care of that you know it's released. So, 3 moles of oxygen. If you notice, we're not really worrying about significant figures. We're assuming these are all whole numbers here. So 3 moles of oxygen. Again, same thing. This is my given. Write it all out. Moles of oxygen. So if I have moles of oxygen on top, go to your balanced equation, find your relationship. For every 6 moles of oxygen, you release 2,560 kilojoules. So if you look at it, you have half the amount of energy. So therefore, you will have half the amount, excuse me, let me try this again. You have half the amount of oxygen, same the answer there. You have half the amount of oxygen is that this balanced equation is showing. You get out half the amount of energy. So again, that's how much energy is released. So let's look at other things we can do to our energy. Well, what if we reverse it? Well, if we want to reverse it, reverse it. So that means your reactants, they're just going to switch places. So I would rewrite it that you're going to be having 6 moles of water. Okay, I'm not really worrying about my states. Hopefully some of you have recognized these reactions from biology. Cellular respiration, we're producing glucose. So where's the energy come from? Photosynthesis. Where's the energy come from? The sun. But it needs energy in order to produce the sugar. And 6 moles of oxygen. So what happens when you reverse it? In the reverse reaction, the energy is going to be the opposite. So it's now positive, and that's an endothermic reaction. So how much energy is needed then to make 12 moles of glucose? Well, for 12 moles of glucose, what do I know the relationship? I know for 1 mole of glucose, it's 2,560 kilojoules. So just take 12 times 2,560. And again, this one, let's just worry about the concept. We're not stressing on the significant figures. We're treating everything as exact numbers. 3,720 kilojoules. We'll start giving you numbers that are more easier to look at the significant figures, and we would have to just round it. If I did want to round this to 2 significant figures, what would it be? 31,000 kilojoules, just if I wanted to round it. Just other ways to get comfortable with the reactions. So I can just give you a reaction like this and ask you, hey, is this endo or exo? Look at where the heat is. Where's the heat? It's the right side of the arrow. You would say that the heat for this reaction would be negative 393.5 kilojoules. This is an exothermic reaction. How do I know? Negative. It's a product. Both of those are telling me the same thing. Compared, look at where your heat is. It's on the left side of the arrow. So you would say that it's a positive 176 kilojoules. You can put the positive or you don't have to put the positive. And I know that this is a endothermic reaction. So being able to look at a reaction where I put the heat, you can tell now a lot of information about it. So a couple problems on the stoichiometry. So calculate the amount of energy involved when 15 grams of water is produced. Notice you have to have a balanced equation. Okay, check. There's coefficients on it, so I assume it's balanced. So 15 grams of water. This is my given. So this is what I have, or you're given. This is what I want. So you have water. Remember though, this is moles. That's 2 moles of water. So I know for every 2 moles of water, I will release 572 kilojoules. But I didn't give you moles. So first thing you're going to have to do in this case then is convert your grams to moles. 18.02. Now go to your balanced equation, and here's your ratio. For every 2 moles of water, you have 572 kilojoules released. So then you can pick up your calculator. 15 divided by 18 times 572 divided by 2. Again, some people may go 15 times 572 divided by 18 divided by 2, however you do it. And this time we will look at significant figures. This has 3, this has 3, so we can have 3 in our answer. So it would be 238 kilojoules. And the energy involved, this is released. The negative means it's exothermic and it has been released. So same concept of what we have been doing, only different step is in your ratio, you can use energy as part of a ratio. Last one to look at. Calculate the amount of energy involved when 3.75 moles of aluminum oxide decomposes. I even gave you a formula. Okay, this one, is this endo or exo? Okay, yes, it's endo. So, look at moles. Probably number one thing I saw in the test, when you made a mistake, you always try to use the molar mass. Look at this, if I have moles, I do not need the molar mass of aluminum oxide because it's already in moles. So you can go straight to your ratio. This is one step. I know for every 2 moles of aluminum oxide I have, it needs 3,352 kilojoules of energy is required. So this is a one step, 3.75 times 3,352 divided by 2. Again, 3 significant figures. So I got 6285, okay, but this is 4 significant figures. So I'm going to round it up to get my 3 significant figures. Okay, that is what we have for today. We will be practicing this, and then we're going to start doing a reaction. Look at the lab and see if we can start calculating some of those. We will see you on our next day.